2018, number 2. Particle moves along the x-axis with velocity given by v of t equals 10 sine of 0.4 t squared for t squared, or divided by t squared minus t plus 3 for time t between 0 and 3.5. And it also says the particle is at position x equals -5 at time t equals 0. The first thing that I would do is, because I'm given an equation, and chances are I'm going to be using this equation throughout the problem, is that my y1, I will type in my equation. Because there are trig functions in this problem, I'd want to make sure that I am in radian mode. Okay, so again, the first thing I would do is type in that equation into y1. Part A says find the acceleration of the particle at time t equals 3. So for part A, for t equals 3, remember velocity and acceleration are related to each other. Acceleration is just the derivative of velocity. So if I want the acceleration of the particle at time t equals 3, then I just want the derivative of the velocity at 3. Okay, so I go math, derivative on your calculator is n deriv, number 8, math 8, d over dx, y1 at 3. So negative 2.118. Okay. There's no units on here. There's no distance measurements. There's no time measurements. So we just leave it as negative 2.118. For part B, it says find the position of the particle at time t equals 3. So let's think through this here. If I take the integral of velocity, what would we get? So we just took the derivative of velocity. If we took the derivative of velocity, we got acceleration. If I take the integral of acceleration, I would end up with velocity. Let's go up a level. Which function has velocity as its derivative? And that would just be position. And so if I take the integral of velocity, I would end up with my position function. So this is equal to some position function. Now, we don't know what this position function would be, and actually I'm going to use x's. So we'll call this v of x dx, and then, no, I won't. Let's call it, because the function we're going to use, or because my position, I'll use x, we'll use some t's here, it's fine. X, or v of t, the antiderivative v of t equals the position function x of t. Okay. So in this problem, it kind of gives us some hints and some clues. We want to figure out the position of the particle at time t equals 3. But the problem tells me earlier that the position of the particle is -5 at time t equals 0. So x is equal to -5 at time t equals 0. So I have two different positions and two different times. Okay, so what we're going to do is the integral, because I have my two different times here, we're going to do the integral from 0 to 3 of the velocity function, and this would equal the position function evaluated from 0 to 3. Okay, I don't want to erase those, do I? Let's kind of drag these off to the side here. Part of my work for reasoning through this problem. Maybe it helps you guys follow along as well. Okay, so the integral from 0 to 3 of my velocity function, if I plug in 3 minus plug in 0, okay, let's see here. So I don't know the integral yet. The position at 3, we don't know. That's what we're trying to figure out. But the position at 0 we do know, which is -5. Okay, so minus the -5 here. Because it's minus -5, I could change that into plus, and then move it over, which would make it -5. Okay, so now I have an equation that represents the position at 3, so I can go ahead and type this in the calculator. -5 plus the integral from 0 to 3 of y1, which is -0.176. negative 1.760. All right, part C. It says to evaluate the integral from 0 to 3.5 of the velocity and evaluate the integral from 0 to 3.5 of the absolute value of v of t. Okay, so let's see here. The integral from 0 to 3.5 of my velocity function. Let's just go ahead and do that. Math 9, 0 to 3.5 of my velocity function is 2.844. And then let's do the same thing, but this time with the absolute value of velocity. Okay, so this time math 9, 0 to 3.5 of the absolute value. Absolute value is math, and then go over to num, which is number 1, alpha trace y1 dx. So this time the answer is 3.737. Okay, so those are my two evaluations of the integrals, but this time it says to interpret the meaning of each integral in the context of the problem. So let's take a look at the first integral. The first integral is just your displacement. This is how far we traveled. No, this is not how far we traveled. This is the displacement of the particles. So from 0 to 3.5, I ended up a distance, my changed distance from 0 to 3.5 is 2.8. That's all that I ended up essentially moving from start to finish. Now I may have moved more than that. I may have gone 3 forward and then a little bit backwards, but this was my displacement. It's the displacement of the particle from t equals 0 to t equals 3.5. Now, whenever I take the absolute value of velocity, that's how much total distance we traveled. Okay, so the integral from 0 to 3.5 is, for the absolute value of v of t, is the total distance traveled from t equals 0 to t equals 3.5. Okay, so that's the total distance traveled. Whenever I take the absolute value of velocity and its integral, then that's the total distance. But if I just take the integral of velocity, then that is just my displacement. So that's how much, it's kind of like that phrase, 2 steps forward, 1 step back. So 2 steps forward, 1 step back. The displacement here, if I went 2 forward and then 1 back, my displacement is only 1, but my total distance would be 3 because I went a total distance of 3 steps. Okay, hopefully that makes a little more sense between displacement and total distance. Okay, part D. A second particle moves along the x-axis with position given by x sub 2 of t equals t squared minus t for t between 0 and 3.5. At what time t are the two particles moving with the same velocity? So we're given a velocity function up at the top, and I want to know at what time are the two particles moving with the same velocity. Okay, so I'm not given a position, I'm given the position function, I'm not given its velocity. So I want to figure out what is the velocity of this second particle. Okay, so I want to figure out its derivative of position. So the derivative here would be 2t minus 1. If I want to know when they're moving with the same velocity, then I'm going to set the velocity from the original problem equal to this 2t minus 1. So on my calculator, I'm going to type in 2t minus 1 into y2, and I'm going to figure out where these two equal each other. So my calculator is still set from problem 1, so I'm just going to go zoom standard, and we'll see what this looks like. I probably want to zoom in a little bit more because this is really tight and I may not be able to see it. Now the bounds on this problem, it says from 0 to 3.5, so on my window, I'm just going to make that from 0 to 3.5 because that's all I need to know. That's all that my graph is situated on. And I want to find where these two equations cross, so I go second, trace, intersect. First curve, second curve, guess, 1.5705. Okay, so t is equal to 1.57054. If we listed them all out, the two particles are moving. They're moving with the same velocity. Whoops. At t equals 1.571 if you wanted to round it up. If you just truncated it and cut it off at 1.570, that'd be fine. Okay. As far as grading is concerned on this one, you would get 1 point for part A, 3 points for part B, 1 point for using this integral, 1 point for using the initial condition, and then 1 point for using, or 1 point for getting your final answer. For part C, you'd get 1 point for this, and then 2 points for the interpretations. And I have a feeling it would be all or nothing, so this would be 2 points total for having all of that. For part D, when you set these equal to each other, that would be your first point, and then 1 point for your answer. Okay? All right, that's it for this one.